Mba633 instructional video prepared by Professor Ahmed Datta, School of Management, George Mason University. This is our fourth segment on the topic of multiple linear regression, and here we'll look at the individual independent variables and look at the diagnostics for those. So just as a reminder, the data that we're looking at is data for football teams in one season, and the dependent variable is the winning percentage, and we have 8 independent variables labeled as you see in the first row. Okay, and we've been in the process of understanding the diagnostics generated by Excel. So in the previous video segment, we had analyzed the ANOVA output and concluded, based on this particular p-value of 0.0000153, that the 8 independent variables collectively are statistically significant. So if I were to use all 8, then that helps explain the variability in the dependent variable y, and collectively those 8 have a statistically significant relationship with the dependent variable. Now we're going to parse the 8 independent variables and see how good or how well each of these 8 are doing in terms of contributing to the explanation of the variation in the dependent variable y. So you remember from our discussion of simple linear regression, and we mentioned it in our first segment on multiple linear regression as well, that these coefficients B0 through B8, these are point estimates of the respective population parameters. So B0, the 1.131, is an estimate, is a point estimate of beta 0. Similarly, B8, this minus 4.4 times 10 to the minus 7, is a point estimate of beta 8. So if you look at each independent variable separately, the hypothesis test that we need to check is the second set. Remember, we had mentioned that in terms of checking whether the regression is significant or not, we first do a collective test. Take all the 8 together. Are they any good? Once we have concluded that yes, we can reject the null hypothesis, not all the slopes are 0, then we try to drill down and see how each independent variable is doing. So for each independent variable, we have a null and alternate hypothesis. The null hypothesis is that the slope corresponding to that independent variable is 0. The alternate hypothesis is that the slope is not, for that independent variable, is not 0. So if we were to take the second independent variable, which is, let me see what that is. The second independent variable is fumbles taken away. So if we were to take the second independent variable, then the null hypothesis would be beta 2 is 0, and the alternate hypothesis would be beta 2 is not equal to 0, and we would very much like to be able to reject the null, because if we do reject the null, then we say that yes, the second independent variable is in fact contributing to explaining the variability of y, because the slope with a very high degree of certainty is different from 0. So let's look at the output, and you remember how I will not do, I think for this, when we went into detail for the simple linear regression, I explained to you exactly how each of these numbers in the diagnostics are obtained. We did the detailed calculations. If you've forgotten them, you can go back and look at that video clip. I don't want to repeat those calculations, but just we'll do some interpretations. All right, so let's take the first one over here, is interceptions taken away. The slope, the point estimate that I get, so this is B1, is 0.01623. So based on that, the question I would ask is, does that allow me to conclude that beta 1, the corresponding slope in the population, is different from 0? And I've told you many times during hypothesis testing that the absolute value of the sample statistic, the absolute value of B1, tells me absolutely nothing. Okay, so I need to standardize. So in order to judge whether this 0.016 is significantly different from 0, I need to standardize. So how do I standardize? I use the standard error of the estimate here. It's 0.00. So this 0.0044 is the standard deviation of B1. Remember, B1 is a sample statistic. I got that coefficient based on a sample of those 30 odd teams that I have for that one season. So 0.016 is a point estimate of beta 1, and that's a sample statistic, hence it's a random variable. B1 is a random variable. It's a so it must have a standard deviation, and Excel has given us what that output is. So if I were to try and find out how many standard deviations away from 0 is this 0.0162, that's what this number tells me, is 3.67. Okay, so just as a reminder from your simple linear regression analysis, so let's divide this 0.016 divided by the standard error. Okay, that's how much one standard deviation is. So there is your 3.67. So physical interpretation is this 0.0162 is 3.67 standard deviations above 0. Now, based on what we know about our empirical rule, namely 68% of values lie within one standard deviation, 95% within two standard deviations, and 99% within three standard deviations, we think it's highly unlikely that this t value would have occurred purely by chance. If the true slope, if the true beta 1 was in fact 0, it's highly unlikely that I would have gotten this in the sample purely by chance. Okay, how unlikely? That's given by this p value. Remember, our standard levels of significance, thresholds of significance, are 1% and 5%. So even at the 1% level of significance, this p value is lower. So I can say, based on what I see in the sample, this 0.016, that with a very high degree of certainty, the true beta 1, this is B1, I'm concluding with a very high degree of certainty based on this p value that the true beta 1 is probably is in fact different from 0. In this case, it's positive. Okay, now, so that's good for this particular independent variable. But now if you look down at the p values of all the other independent variables, not all of them are doing as well. Take this one, there's fumbles given away. You can see the p value is 0.54. What does that mean? It's saying that this would be, let's see, x1, x2, x3, x4. This is the fourth independent variable. So what this p-value of 0.546 is saying is that if beta 4, the true slope, the true coefficient of x4, if beta 4 was in fact 0, there is a 54% chance, okay, that I would make a type 1 error by rejecting that proposition. Okay, so for the fourth variable, the null hypothesis would be beta 4 equals 0, and the alternate hypothesis would be beta 4 not equal to 0. So what this p-value is saying is, based on what I see in the sample is telling me that B4 is 0.005. So I'm seeing B4 to be minus 0.005. By looking at that, if I conclude that, hey, this value, so that if I conclude that that I reject the null, in fact, which is beta 4 is equal to 0, if I reject it, there's a 54% chance that I'm making a type 1 error. In other words, I cannot reject the null with any reasonable degree of certainty. Okay. Similarly, if I look at field goal percentage, you look at the p-value of 0.999. Essentially saying is, if the null were true as an equality, namely if beta 8 was in fact 0, there's a very high likelihood that I would get such a sample statistic purely by chance. Alright, so if you look at all the high p-values, let's say we assume an alpha of 5%, a threshold of 5%, let's be generous and we'll assume an alpha of 5%. These variables, this is x2, the second independent variable, the fourth independent variable, the eighth independent variable, these are all suspect. What these p-values are saying is that if each of those population parameters, namely beta 2, beta 4, and beta 8, if they were 0 on their individually, there is a high likelihood, there is a reasonable likelihood that I would be getting these sample slopes purely by chance. Okay, so I would be nervous about rejecting the null hypothesis that the true slope for those coefficients, for those independent variables are 0. So even though collectively, my collective analysis was, if I take all 8 variables together, then they're helping to explain the variability in the dependent variable y. When I parse the 8 variables apart, I can see that not all of them are contributing equally to the explanation. In particular, field goal percentage, fumbles given away, fumbles taken away, and I would also say rushing yards per game. These are all suspect. These 3 variables that I've just identified, or 3 or 4, are probably not contributing a whole lot. Okay. So my next step in getting a parsimonious model was to try and remove these variables, maybe remove field goal percentage from the regression and see what sort of results I get um, with that particular independent variable removed. Okay, and I keep doing this serially until I reach a conclusion that I have been able to explain the variability in the dependent variable reasonably well, but I have not too many independent variables. I have a relatively parsimonious model. So that's a topic for another discussion, that is, how do you end up with a good model. My aim over here was simply to point out how you examine the independent variables separately. So the ANOVA analysis over here is a collective analysis of the significance of the regression as a whole, namely taking all of the independent variables together collectively. Do they help you explain the variation in the dependent variable? But that doesn't mean that each variable is doing an equally good job. That's when you look at the independent variables separately, look at the p-values, and then determine which ones are not contributing a whole lot, and they're candidates to be removed from the regression. Now you cannot remove all of these, you shouldn't rather remove these independent variables all at the same time. You do them one after the other, because every time you remove one independent variable, all these diagnostics will change. So you want to do them one at a time and see what effect that you get. Based on the p-values that I see in this column, my first variable, the first independent variable that would be a candidate for removal, is field goal percent. I would remove that, see what regression equation I get, what p-values I get, and then go on from there and perhaps make the model more parsimonious.